friends, what's up? I'm back. This is a supplementary video for Chem 1C, and my name is Haley Larson. There are two other SI leaders for this course, Karen and Samantha. All questions can be directed towards me for this video via email or asking for my Zoom ID. And all credit for the worksheet and questions about the worksheet can be directed towards Karen. In this video, I will be reviewing the second worksheet that's posted, so we can get started. Make sure to pause the video when you believe it's appropriate for you. So at 1045 Kelvin, the partial pressures of an equilibrium mixture are these numbers respectively. Calculate the value of K of partial pressures at the specific temperature. So I think the first thing we should do when we see anything having elements in it is make a balanced equation. So for this balanced equation, it would be the creation of water or the dissociation of water, whichever one you want to do, it doesn't matter. So I'm going to do the creation of water. So that would be H2 gas plus O2 gas becomes H2O. Now, we can't leave the equation looking like this. Why? Because it's unbalanced. And in order to balance it, we would have to put a 2 here, because the oxygen is imbalanced. But when we put a 2 here, we also have to put another 2 somewhere else to compensate. So we could put the 2 over on this side for your hydrogens. Now that we added coefficients, the equation is fully balanced. So we can start trying to find our K of partial pressures. So Kp equation is just like your K equilibrium constant, except it's based on pressures this time instead of concentration. So this would be partial pressure of the product. So this is partial pressure of H2O, our product, raised to our coefficient, which is 2, over our reactants. So that's the partial pressure of H2 raised to the coefficient of 2, and partial pressure of oxygen raised to the coefficient of 1. Now that we have this equation, we can plug in our values. So that would be 0.04 atmospheres raised to the second over 0.0045 squared and 0.003 to the first power. I forgot to add atmospheres here. There's one for that one as well. So we can plug this into a calculator and we would get something close to 2.6 because there are 2 sig figs times 10 to the 4th. Our units would be in atmospheres to the -1 because we could cancel out 2 of the atmospheres. And this would be at our chosen temperature of 1045 Kelvin. So for number 2, we have 2 equations that we need to combine in order to find the overall value of K. So we're looking for the K equation. Remember, the K equation is based on concentration of products over reactants. So first, I'm just going to add both of the equations together in order to see if things are cancel out. So that would be 2 carbon plus 2 oxygen gas becomes 2 CO2. And on this side, we have 2 CO2 becomes 2 CO gas plus oxygen gas. So if we add these two together, we can see that carbon dioxide on this side cancels out with the carbon dioxide on the other side. You can also see that one oxygen cancels the oxygen on the product side, which makes this oxygen just 1. And when we add the equations together, we get 2 carbon solid plus 1 oxygen, equilibrium arrows, 2 CO2 gas. So in order to write the K equation for this, we're going to put the products over the reactants. The product being concentration of CO, and this is raised to the 2nd power because of its coefficient. Then on the bottom, we have solid carbon and gaseous oxygen. Remember that the concentrations of solids and liquids are constant. So therefore, their concentrations can be replaced by a 1 when it's in an equilibrium expression. So I can either put a 1 here, or I can leave it as nothing for this carbon. And I can add our oxygen to the bottom with a coefficient of 1. And that would be the K overall. So for number 3, we're determining the direction of the reaction. Remember, reaction quotient and K are the same. Q, the reaction quotient, is still, just like K, equal to the products over the reactant. So let's just start with the middle one. So that would be part B. Remember that products over reactants is the ratio at equilibrium. So we're looking at how the ratio is different in Q versus in K. So here, if Q equals K, then the ratio is the same. If the ratio is the same as equilibrium, then there is no reason for the reaction to progress in any direction. So for B, we could put no shift. So how about for A? If Q is less than K, how would we get a Q that is less than K? Well, let's pretend our K is equal to 1. If our K is equal to 1, we need to have a Q that is less than 1. In order to have a Q that is less than 1, we could mathematically increase the amount of reactants or decrease the amount of product. How does that make sense? Well, if I put more reactants in the equation, so if I have 1 micromole or 1 mole of products and I have 2 moles of reactants, therefore adding more reactants, then our value is 1/2, which is less than our K of 1. But for this ratio, in order to make it 1 again, because we're always trying to reach chemical equilibrium, we would have to reduce the amount of reactants and increase the amount of products. And we could do this by subtracting and adding 0.5 if we're going to get really mathematical about it. So if I subtract 0.5 of the concentration of the reactants and put it to the products, then I could finally get our ratio of 1 again, and that would be equal to K at equilibrium. So how did I get back? Well, I increased the amount of products and decreased the amount of reactants. I relieved the stress on this reaction by creating more product. And when we create more product, that means we're moving in the forward direction. So for A, we would move in the forward direction if K is smaller. If Q is smaller than K. So for C, you can imagine it would be the opposite of this. So if I have a Q that's 2, that would be effectively 2/1. That's still greater than K, which is 1. And in order to fix this to get back to equilibrium, I would still put 1.5 and 1.5. But the 0.5 is being added to the reactants instead of being added to the product. And because I'm adding more reactant and taking away the product, that means the direction of the reaction is going in the reverse. So for our last question, what is Le Chatelier's principle? What are the factors that can cause stress in the system? Remember that Le Chatelier's principle is basically trying to relieve stress, always knowing that a chemical equilibrium or a reaction that has a chemical equilibrium will always try to move towards the chemical equilibrium in a way that relieves stress. This, of course, is linked to delta G minima, because a chemical equilibrium is always at a delta G minimum, meaning that it is always the most energetically favorable position for that particular reaction. So if something perturbs this chemical equilibrium, which is in the favorable position, the chemical equilibrium reaction will always try to go back to itself in order to be energetically favorable. So ways that we can perturb this or cause stress for the system would be adding or removing products or reactants. This is the same concept that I use in question 3. Also, we can increase or decrease the volume or pressure that the system is inside. This would cause the equation to shift, and as I said before, it would shift back to the most favorable position at the delta G minimum, which is chemical equilibrium. All right, so thanks for watching. That's it for this video. Make sure to sign in using the attendance link in the description below. Any questions that you have can be commented or emailed to me, and I'll see you guys next time.